All right. Hi, everybody. Welcome to the first class in how to do useful things in Python. I'm Dave Tabb, and I don't know Python very well. But I think that gives me some useful insights. I have long programming experience in everything from BASIC to assembler to Pascal to C++ to Java. I've programmed in a bit of everything over time. And my hope is that I will be able to recognize for you some of the things where Python is a little weird and help you get to a place where you can use it to do useful things. As I mentioned in the first message to everybody, the point of these 6 sessions will be to get you to a place where you can write a pretty simple bioinformatics tool. In this case, we're going to open a FASTA sequence database of amino acid sequences, count how many of them there are, and report how frequently each amino acid is used in that database. That may sound really intimidating, or it might sound really easy. If it sounds really easy, do you want to be an assistant? Well, we're lucky that Darren Zimri, I got the emphasis in the wrong place, sorry. Zimri is going to help us with getting everybody's laptop working. The goal, as I've said, is not that you watch, but rather that you are able to do this programming yourself. So I've already, I suppose everyone has watched a cooking show where somebody does something very complex on the tabletop, and then they put it in the oven, and then they reopen the oven and take one out that's been cooking all that time. In the same way, in this particular cooking class, I'm going to try to show you where we want to end up each day. So you can see that in the files that we've made accessible here, we have one called 2019-0510 goal1.py. So my goal is that we write that today. And I'll try to explain how we get there from here. But I've copied these on my computer into a directory called, right off of the C drive, called SunPython. SunPython. So I'm going to assume everybody puts it in exactly that same place. If you put the files in a directory on your desktop, we can still get there, but you'll have to remember where you kept your files located, because I can't keep track of where everybody has their files located. So if it's straightforward for you to do, it's useful to have the files that we're copying from the Google Drive in this directory, SunPython. I've just spelled it S-U-N Python. All right. I hope you don't mind. I'm going to start with a couple slides because I think that a little bit of perspective can be useful. One of the first questions you get from somebody who is trying to learn how to be a programmer is, which language should I learn? And ultimately, this question is one that produces a fair amount of heat, but not a lot of light. Because the answer is that most of the programming languages that exist out there are pretty good at getting basic things done. And in many cases, bioinformatics is just about getting something done. If you're talking about some of the very high-end algorithms that we use, like de novo assemblers or something along those lines, you really need to write for great efficiency and ability to deal with relatively small amounts of memory for a really large amount of data and so on. If you're doing something like that, your choice of language is going to matter an awful lot more than if you're writing something that's handling some text files. And an awful lot of what we do day to day as bench biologists or bench molecular biologists or human geneticists is dealing with text files. When we think about things like FASTQ files, these are the output from sequencers. They're just big text files. If you're dealing with a SAM file, it's just a big text file. So there are lots of times, and certainly FASTA sequence databases count as just text files. So a lot of what we do day to day is going to require that we can read a text file, do some sort of reasoning on it, and have some sort of output. So that's what we've modeled this around. In 6 sessions, in 6 hours basically, we're going to get from no knowledge to the ability to read a text file, do something on it, and get done with it. Now there are lots of languages out there. This is just a very small sampling. The world is not limited to a simple 7 languages. but these are pretty big ones that get used for scientific computing a lot. Now, when I was in graduate school, I decided that I needed to learn a language that was pretty adaptable to a large number of uses, that would be good for writing open source software, that would let me do development of object-oriented programming. I thought it would be really great to learn a whole bunch of new programming skills. So I learned Java. And Java is really great for a lot of purposes, and the world has a lot of people with a lot of talent in these spaces. There are a lot of useful libraries for it, which lets you do complex operations by using somebody else's code, in effect. And it's a very nice tool. So Java is actually one of my favorite languages, and in a lot of respects it would be easier to teach you that than Python. But instead, we're going to teach Python. Next, some people have heard of .NET. .NET, does that ring a bell with anybody? Some applications that we write for Windows. By the way, if at any point you need to talk with Darren, just raise a hand in the sky and we'll get him over there. But we want to make sure everybody can move along as we go. Is the download of Python working okay for you? Brilliant, that's good news. Okay, a lot of people use .NET programming to produce very nice looking Windows utilities. And so one of the nicer languages for doing that is one called C#. C# has a lot of similarities to something like Python, actually, and again, it's a very useful language. I'm happy to talk to you about how to use that for various purposes. It has a lot of, it represents what would happen if C++ and Java had a baby, I think. Then we get down to something like C++. A lot of people will say that you have to be a pretty hard-nosed programmer to learn something like C++, but in fact, it's a very versatile language, and it is what the beginning programming classes were taught in at the university where I went. So I don't think of it as that challenging a language, one that is inaccessible to everybody. But there are a subset of programmers, some of whom have very impressive beards, who use Fortran. Fortran is a really great language if you're doing some really big, hairy mathematical problems, because there are some uber-fast libraries that have been created for dealing with very large mathematical problems. If you're into matrices, Fortran is probably your friend. From there, we have languages like R. R is probably the language I used most from day to day, and R is very good if you're into biostatistics because it supports everything you would want to do, and quite frankly, quite a few things you would want to do in the space of bioinformatics as well. So Bioconductor has made R quite a heavy-hitting language for the practice of bioinformatics. There is a language up here that I strongly dislike. It's kind of in bad taste for me to say this, but I consider Perl a write-only language, which is kind of a rude joke to make about it. What I'm saying is that somebody who writes a Perl tool is typically writing something in the language they happen to be good at, and they get something done, and they get it to work the first time, and then they abandon the code for a month or two, and they come back to it and try to do that same thing again, and discover they can't figure out how to make that code work again. So Perl is a troublesome little language, and I have a very irritated relationship with it. But there are many people in the world who use Perl for bioinformatics every day, and a lot of them are able to perform miracles because Perl has a multitude of ways to accomplish any single task. People who have their favorite tasks, favorite methods of getting something done, can get something done very, very quickly. So I'm sure that somebody will comment on this YouTube video saying, I could use Perl to do what you're doing in this 6-hour class in 5 minutes, and they would be right. It would be right. And finally, we get to Python. Now, Python has developed kind of an odd reputation, I think, as the go-to language. It is the language that we use to move forward with big data. And we were launching a new track in our honors program called Data Sciences that was going to have a rather longer, in-depth look at the language. But instead, we're going to do just these 6 sessions. So I appreciate that. Data science is a thing, we say. Big data is a thing, right? These are what we're told again and again are going to get lots and lots of funding, and people seem to think Python relates to this very strongly. Python, for example, is one of the most popular languages used for things like data camp and things like the Square Kilometer Array project. So that is it has drawn a lot of attention very quickly, and I'm going to try to talk about some of the things that I find distinctive about it. First off, I am very accustomed to languages that I compile. What this means is that if I want to try out my code, I have one step where I dump my source code through a compiler, and this creates an executable program. That executable program I can then run. But the process of compiling doesn't run it. So I have to do the compilation, then I can run the software. That's a two-step process. Interpreted languages are really, really different. Your computer does not, by default, know how to run Python software. It just doesn't. Now that you've installed Python on your machine, you have an interpreter in place. That's what we have installed by downloading and installing that. So, in effect, what we are going to do is create a script. We're going to look at Python in an interactive mode, but the way that we would use it for a big project is that we would write a script that represents our program for the software to follow. And we'll encounter that interpreter directly in just a minute. There's a big emphasis in Python on making readable code. This is a really, really big deal because a lot of times we find that people have written code that's very unclear. So in the Python context, it's a bad idea to use a variable name like x, because x doesn't tell you what it does. It just says it's a variable name. Do you know if that's a string? Do you know if that represents the value of pi? Does it represent a counter for a loop? We don't know. It's just x, right? So in the Python world, there's a strong emphasis on people calling a variable something that is memorable in how it functions. So we will encounter that as we move along. One of the things that I find most jarring about Python, and which actually endears it to a lot of people, is that we get rid of curly braces. I am very accustomed to using these little curly braces for things like while loops to say, while some condition is true, repeat these blocks of code. But the thing that you run into if you use a lot of curly braces is that you end up forgetting how many open braces you have and how many closed braces you've got. And if you can't keep track of which brace is opening a section of code and which one is closing that section of code, you can get really lost in trying to debug your code. So instead, Python has a very strong emphasis on where things are positioned on their lines. So that's a little odd. And am I misstating anything there? Okay, I saw your eyebrow move. I want to check. He's my expert in the room, so all right, this is good. So I've included one additional line here that's kind of an absurdly technical detail, but I think it's worth talking about. I mentioned that hi, come on in.
Hi, I'm so sorry to interrupt. My ECC and GN's in these fees. It's going to be a bit late, please let us wait.
Okay.
Sorry.
Cool beans.
Quite late. I'm sorry, it's my fault.
We'll survive.
It's me so hot.
Righto. So, I've written here that just-in-time, JIT, just-in-time compilation is possible in something called PyPy. So this is an odd little feature. It might be that you've written some Python code that works great, except that it takes all weekend to run, and that might be very irritating to you. So one of the disadvantages of an interpreted language like Python is that it can be relatively slow when you have a big computational job to do. So it is possible, when you have a program that works fine in interpreted form, to compile it so that it runs at the speed of native code, which is, again, a bit of jargon, but let us say, instead of running over the weekend, could run in a couple of hours. So that kind of benefit is really powerful and allows us to sidestep some of the problems of an interpreted language. Now, I have one other figure here that is a really important one. And I think that my friend Gerard Trump would be very sad if I were not to include it, which is to say that every programmer at some point needs to be able to break up a problem into small, solvable pieces. That is a really, really big deal. Being able to abstract a big problem into a set of small problems is hugely important. Okay, so we're going to start then with we're going to start by a conceptual planning of how our software is going to work. So can I guide people through this? I'm going to talk really loudly so it shows up on the recording. Pardon me for yelling. All right. So I have used a total of 3 different kinds of shapes on this diagram. We have our little purple blobs. These represent start points and end points. And you can see that although this software is going to start just one way, it has 3 possible ways that it can end. So let's start with one of the essential rules of writing good code. One of the essential rules of good code is that you should be able to give some sort of guidance to a user who has never encountered your tool before and has no idea how to use it. This is the usage information. So we see that in this case, we're going to start with this purple blob at the top, and then we're going to move to a decision. Anything that's a blue diamond here it could represent the fact that you enjoy Lucky Charms cereal as much as I do. Everyone remember blue diamonds, right? Okay, well, here we go. This blue diamond says, is a FASTA name provided? We want our software to be useful to people who are doing something other than this problem right now, which means that we are going to accept as input at the time someone runs our script, what is the name of the FASTA sequence database that you're going to operate on. Okay? So if a user simply runs our software and doesn't supply a FASTA sequence database name, we want the software to output the usage information, which is kind of our most basic documentation that says, how do you use our code? We want to output that usage information, and we want to terminate right away. Okay, so this is not doing much, but adding that functionality means that somebody who's using our code for the first time will get some sort of information about how to use it if they simply just run it with no parameters. That is a very powerful thing to do. And you'd be surprised how many graduate students have written code that doesn't follow that basic rule. You, as a user of your own code a year from now, will be very glad that you wrote in some basic documentation that says, no, that's not how you use me. Outputting usage information is important. This helps you too. So we see that there were 2 options coming off of the blue diamond here. And in the other case, we see that the FASTA file name was provided, and we come down this leg. Okay, so now we have a parallelogram. Now, I lived in Nashville in the United States. Does everyone recognize what this shape looks like in terms of the United States? A baseball diamond. Well, actually, these blue ones are a little stretched, but this parallelogram is very, very similar to the state of Tennessee. Memphis would be down here. Here's Nashville right in the middle, and then here's Knoxville out east. I lived in multiple places in the state. Anyway, so these parallelograms, these little Tennessees, help us to talk about individual processes. So we have a process that says, having received a FASTA file name, we're going to open that FASTA and read it. Now, it could be that the FASTA is readable. That's a really good thing, right? I mean, if you can actually open the file and start getting information from it, that means you can go ahead and do the good stuff. But, and this is a really important thing, you must realize that your users, the users of your software, they're tricky people. And sometimes they're going to pull little stunts on you. What's the most obvious thing that could go wrong if somebody provides you a file name and you try to read it? What's that? Not written correctly. Okay, so that's one problem. It may be that they've given you a file, but it is not a FASTA format file. Right? So that would be a problem. But there are some even more basic problems than that. Somebody want to tell me the big glaring one? What if they tell you, I want you to read protein.fasta, but that file does not exist? Or what if they've mistyped it? Maybe they typed it with protein.fasta all in capital letters, but the file system only has a file where it's all lowercase. Right? These are equally big problems. So we have to protect ourselves against the users because the users are out to get you. Always cultivate an atmosphere of paranoia about what your user is going to do to your code. So we see then that the FASTA is readable actually takes into account several things. One would be this sequence file exists. The other one is things like this file is legible by me, by Python itself. There are lots of things that can go wrong here. And of course, at the end, we need it to be formatted correctly. Some things we can trap for and some things we can't. So when I say the FASTA is readable, I have a lot of things going on here. But let us say that they've given us a wrong file name. It doesn't exist. Then we need to pop over here to no, report that error, and again, die, right? So this is our second outage. Now from here on, I'm going to make the assumption that everything is going smoothly. So they provided us a FASTA file name. That FASTA file name is readable. And so we're going to do this complex operation of reading the next protein sequence. Okay, now there are multiple steps to reading a protein sequence off a FASTA file. What's the first thing I should see for any protein in a FASTA sequence database? First character. So maybe you haven't looked at the FASTA files yet. This is good. Okay, well, I'll just tell you that every protein in a FASTA file starts with a greater than symbol. It says, this is the name of a protein, what you're about to see. So you'll see a greater than symbol, and then you'll see an accession string that is the name of this particular protein. Then there's a white space, and then there's a whole bunch of text. What people put in that text can vary a whole lot. It could say, similar to hemagglutinin, blah, 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 blah. It could say, hypothetical protein. It could be completely blank. FASTA creators do all kinds of crazy things. But the sequences only start on the line after, right? So you have a line saying, I'm a protein, this is my name, this is my description. Then the following lines are sequence. Do we know how many lines of sequence we get? We do not. We keep reading until we either hit the end of the file or we hit another greater than symbol. Well, this will become clearer when we actually look at the FASTA file. But I just want to say that we're going to read here the next protein sequence. So, having attempted to read a protein sequence, we should ask, did we succeed or not? Did we get a protein from that effort? So if we have some math to do. So remember that the tool we're writing is going to count how many proteins there are, and it's going to tell us how frequent each amino acid is in that database. So we need to update our statistics once we have a protein sequence that we've read. And then we attempt to read the next protein sequence. So you see, we started this off by reading the next protein sequence. Having dealt with this one, we try to read the next one, and then we ask again, has the sequence been read? Generally speaking, a protein sequence database has a whole bunch of proteins in it. I've given you a copy of the Mycobacterium tuberculosis database from Ensemble. So it's something like 4,000 proteins, which means that we're going to be running literally this little loop 4,000 times. It's going to keep circulating around here and again and again and again, and finally, it's going to attempt to read a sequence, and instead, it's going to hit an end of file. Sneaky, huh? We go trying to read a sequence, but there are no more sequences in this file. At some point, all good things must come to an end, and we come out this back end here. Finally, we see we're going to output our FASTA statistics to the screen and die. It was a brief life, but it was well lived. Lived to the full. Okay, so that's our goal. We have 6 hours of time to do that together. It's going to be fun. Okay, and I have to say, we're all going to learn a lot from it, so I really appreciate your coming. So I'm going to put away that interface for a moment, and we're going to look at our Python tools. Now, I would point out that the goal script that I've created has an extension on it. Did everyone spot that? That .py business? That's very helpful, primarily to the programmer, in letting you know what kind of software this is. If I had created a C++ program, I would probably have created it with a CPP extension. If I were writing in Java, I would write a .java program. If I'd written Perl, it would probably be .pl. In this case, I'm using .py because that's what lots of people use to indicate files that should be run by a Python interpreter. But where is Python? This is one of the things I find most puzzling about the Python interpreter. Having installed the software, trying to find it is a bit of a hunt. So I'm going to start by hitting the Windows key and typing Python. Now, you may end up with a variety of different tools all showing up on your desktop at this point. I would see that Python 3.7 64-bit is a pretty good bet. That is a desktop app. I'm going to take a quick look at its file location. Everyone sees that? So if I click on this, I see that I have a variety of files that it has found. It's found them in a really odd directory, hasn't it? Look at this. C, users, dtab, that's me. App data, roaming, Microsoft Windows, start menu, programs, Python 3.7. Is that where the software really installed itself? I see a head shaking back there. You're spot on with that one. So what we see is that we have things like Python manuals installed, very helpful if you're learning a language. We have module docs, also very helpful. We have idle, I'm not even sure what that is at this point, but we'll find out. And we have Python 3.7. But I would note, if you have the 32-bit version, by the way, don't worry about it, it's fine. It'll work just great. But you see that they've got these little arrows at the lower left in the icon, which is a clue to us from Windows. That's not really the program. This is a shortcut pointing to the program. So we still haven't found where Python is hiding itself. So let us now come to Python 3.7 and right-click that again. Okay, you should see on this menu, Open File Location again. So I'm going to click that. So it started in my Start menu. Now it's in an altogether different location. Now it's in C, Users, Data tab, App Data, Local Programs, Python 3.7. This software has installed itself under my user account. Oh, we had a hand up. Do you want to ask a question of everybody, or do you want Darren? She wants Darren. See, I was pretty sure that this is something that was going to run people afoul, because trying to find this software is really bedeviling. Okay, are people able to find the software on your computer? Have you been able to get to this place? Oh, this is good news. You guys are so good. All right, I'm going to make sure that this is actually running properly. I want everybody to run off the Start menu. Just type CMD. You should be able to start a command prompt. Is everybody able to do that? CMD. We're going to do this because we're going to run Python on the command line. It's going to be a great experience for all of us. Any bioinformaticist worth his or her salt has got to be able to run stuff on the command line, because many of the tools we use depend on command line interaction. So we're going to do it. We're going to have command prompt open on your machine. Yours will probably look a little different than this because I've hit enter a bunch of times. But I would note that we want to get you into the directory that contains our software. Okay? So if I do this properly, I'm going to exit this for just a moment. I'm going to restart command prompt. There we go. Now the font's a little small for you guys to read, so I'm going to fix that in a quick hurry here. I'm going to edit my properties. I'm going to go to a bigger font size. Consonants, okay, that's fine. Well, how about I make a really big font? 24 point, okay? Whoa, it's so big. Okay, that's going to work. There we go. So I now have my command prompt open. I want to move to the directory that I created to put the Sun Python code in. Does everyone remember where that is? It's right on the C directory, right on the root directory of C. So if I weren't already on C, I would type C: and hit enter. I'm already there, so it doesn't change anything. But I want to change to C. I want to change directory CD /SUN. Now, what is the defining characteristic of programmers? The defining characteristic of programmers is that we are lazy. Now, I know that the directory name starts with Sun, but there's something that should come after it. So I happen to know there's only one directory on this computer that starts with SUN like this, so I'm going to hit Tab. You see that? Yeah, hit the instructor. That's good. I like that. Yes, my name is Tab. Thank you. Yes, by hitting Tab, I have the software guess the rest of what I'm about to type. So I typed Sun, and the computer said, oh, if he hit Sun and then hit Tab, he probably means Sun Python. Oh, Tab, yeah, it's on my keyboard a couple letters below Escape. Okay, and having hit Enter, I'm now in that directory. Is everybody able to open command prompt? Okay. Those using Linux, you're going your own route. I appreciate that. Well done. Okay, so, all right. I see a head shake. I'm going to check in here. How you doing? Command prompt, that's good. Are you able to move in command prompt to where your files are located? No? Did you put them in the same directory in SunPython? It's on the desktop. Okay. Type cd desktop. No, just type the word desktop. D-E-S-K. Oh, sorry, one space. D-E-S-K. Hit tab. Good. Enter. All right. And do you have another directory inside there? Oh, it's right there on the desktop. Oh, okay. We should be fine then. Great. Are other people able to get to the right place in command prompt? Okay. And the easy way to find out if you're in the right place is to see if the files are there. That's dir, the directory. So you should find the files you copied in there. Everyone doing okay? Okay. Yes, how can I help? Okay. Do you have command prompt open? Oh, so you've executed the software directly. Let's start command prompt by cmd. There you are. Okay. And now you can change to the directory. So you probably need to do cd /sun_python if you use the same location. Everybody doing all right? Yes? Yes. Oh, it's a Mac. It's a Mac. Okay. So you will have, you need to get to that directory somehow. It's going to be a little trickier. Darren, do you do this on a Mac? All right, we'll figure it out. I'm going to show you guys a little trick here that is sometimes useful. Remember, we don't like typing stuff out because it leads to all kinds of mistakes. So I just wanted to point out that, maybe I had Explorer open. Right. So let's say that I wanted to go to a directory on my desktop. I have some here. Oh, maybe Bredasdorp. Right, I took a vacation in Bredasdorp, so I have a directory of Bredasdorp on my desktop. So if I wanted to go there, I could type cd space, but here's the tricky part. Instead of typing Bredasdorp, I'm going to drag that folder from here to there. You see that? And just magically, it entered the whole path name right there. Yeah, that's a lot easier. That might actually work on the Mac. Okay. And yes, on a Mac, you're going to be opening a command shell much more like Linux than you would on here, but very related. Okay. Now, it might seem that it would be really great now to simply run Python here, and you might guess that the easiest way to do that is simply to type Python. But because I didn't follow through on the very last step of the installation, it was kind of a hidden feature. It's not part of my path. On a Windows computer and on other computers as well, the computer knows where to look for normally used applications. That's called the path. But by default, the Python installer does not automatically put itself on the path. But remember, we just looked for where Python was located. See, I still have my this tool open here. I was doing all that stuff to find file location, and I finally got to this location: C users, David tab, app data, local programs, Python 3.7. So what I'm going to do now is tell command prompt itself that I don't want to run just any Python out there. I want to run the Python in this directory. See that? So I can now grab Python exe, drag it over here, and the software now knows where to find that tool. So if I hit enter, I actually get dropped into the Python interpreter itself. So I would like you to drag Python exe from the window where we found it in the file locations onto the command line here. And you should get a result like that. Let's see if this is going to work for people. It's a whole lot easier if Python is on your path, but I haven't set it up that way. Okay, good, well done. Made it in there? Not yet, not yet. Okay. I'm going to repeat that option on here. Let me see. So if I type quit, so I have my command prompt like this. I have the directory where Python is installed, and I can tell this is the one because Python exe doesn't have a little arrow beside it. The little arrow means it's a shortcut instead. If you wanted to find where Python was, you can open its file location from this menu. And then you see it's a shortcut. You right-click that and open its file location again, and you will find it. From there, I can simply drag Python exe to the command line. Just like that. This was the #1 thing that was going to cause a problem today. So if it's not working for you, let's see what we can do. You have Python running, brilliant. Python is running, great news. No computer, buddy up. We have people here with laptops. Okay, all right. If writing works for you, you're running. Good, good. Ashley, Python is running. This is so good. You guys are good. Okay, Python running, Python running, Python running. This is good. How's the back row doing? Running on a different sheet. Oh, here it is running here. Good, yes. How about you? Oh, you installed the whole environment. My goodness. Well, you'll be in good shape. All right, yes. How you doing? Okay. All right. Let me help you on this one. Okay, so there's some Python. That's good. Right. Sorry, right-click that guy. May I borrow for a minute? I swear this is the hard part. All right, open the file location. Here's Python right here. Okay. I'm going to drag this guy, drag him over there. Golden. There you are. Okay, so it might be useful to write that down in a text file or something. Where do you find Python? Because otherwise, we'll end up having this treat each day as we go through class. So if you're able to start Python interpreter, that's great. Caitlin, doing all right?
We'll figure it out.
Figuring it out, okay. Come get it. Okay, I would like to start looking at the code that we want to run, if that's all right. We have a moment, okay? Yeah. I don't even know what's wrong with it. No, I'm not sure what that's, what you're looking at that. When you go to the command line and you type Python, what happens? You moved it to a new location. Oh, we didn't want to do that. If you open a command prompt, a terminal, or a shell, I'm not sure which it's called on there. Does anyone remember how to launch a shell with keyboard shortcuts in a Mac? Is it like Option T or something? Control T? Actually, just down the bottom. Sorry, right? I'm going to just point right up. The terminal, click on terminal. Yeah, type Python. Ah, you're golden. Okay, good news. Python is installed well on your Mac, and you don't have to worry about the path thing at all. You're very lucky. Okay.
That's why I didn't want to override it because it was already like programmed.
Yeah, it was installed right to begin with. That's always a plus. Okay, I want to walk people through the code on screen. this is a Friday afternoon. Time is precious, and I don't want to run us past 4 o'clock. I hope you don't mind. If anyone really wants to stay till 6, you'll be by yourself. I'm sorry, I don't have the heart for that. Okay, but we'll try to walk through this. One of the most basic things that we can do is to interact directly with the interpreter. Okay? What I'm showing on screen is a script. But if I'm interacting directly with the interpreter, it's going to try to this is what we speak of as an interactive mode. The interpreter is giving me this greater than thing as a prompt to say, what am I supposed to do? All right? So let me start by what is kind of a first rite of passage for anyone learning a new programming language, which is the Hello World test. So the simple thing to do is to type print, open parentheses, double quote, hello, comma, I insist on the comma, world capitalized, exclamation point, double quote, end parenthesis. And like magic, we have executed our very first Python program. Okay, so this is an interactive example. This is an interpreted language. We have given it the instruction that it is to print, but it's not to print just anything. It is to accept as the input to print, hello world. And you see that it's got double quotes on either end. We sometimes call this a string literal. That's a very forward way to say it, though, I think. Here we have a function, print, and we are providing it the parameter hello world. And the function print has as its output whatever you fed it. We fed it hello world, out it spits hello world. So if you have a Python script that includes the phrase print whatever, that's what it's going to show. The difference is that when you're running a script, you don't see the command to print that appear before you. You only see what the software chooses to make public, right? And print is to say, spit out to the terminal whatever I tell you to. So if I had a program called Hello World, I might run it on the Python command line, and out would pop Hello World without showing the phrase print Hello World. Okay, so we can also do some basic things like math, right? So if I wanted to say 5 plus 6, it would return 11, because the software handles these expressions in that way. Generally speaking, we find most programming languages end up spending a fair bit of the first day talking about variables and types. For example, we have floating point numbers, and we have integers, and we have characters and strings and things like that. I'm not really going to bedevil you with that stuff. So we're going to sort of take it as read. What happens if we say something like print 5 plus 6? Again, the software knows how to do that. What if I want to do a bit of math right in here? What if I say something like print hello space quote plus 5 plus 6? Aha! We have produced our first error. Aren't we excited at that? Right? So here we are doing something sneaky. The software says there's an error, and it's giving us information about what kind of error in this traceback. It's a type error because we cannot concatenate a string. We can only concatenate a string to a string. Now that might seem a little weird, but let's start by why it thinks we want to concatenate anything. What does it mean to concatenate something? Jam it together, basically. So we might have thought this should reply hello 11, right? You might think that's what's going to happen. But the software realizes 5 plus 6 is a number. It's the number 11. The stuff at the left, hello, is a string. And you can't just jam stuff together like that. So if you're going to have the software recognize, report the number 11, we have to specify, look, I know this is a number, just treat it like a string for just a brief moment. So I can say str right here, and now the software recognizes that those numbers are actually strings. They can be handled as strings of characters. Okay? Yes, there's a question right here. I see it. How can we help? If you have a question, everybody has a question.
No, sure, it was like spot the difference, but I spotted it.
Ah, okay. Yes, the only difference was that before I told it to combine a string with a number. In the lowercase, I told it treat this number as a string, then add it to the other. That was okay. All right. Now, I'm going to look through the code for just a minute. There are some messy things in here. And I want to point out that I don't know this language, right? So there are some oddities of how it treats stuff. I have to look it up, right? So before I come to class each day, I'm going to be checking this code and making sure that I'm building something sane. And he's going to check me to make sure I'm writing stuff that looks like Python, not like a lapsed Pascal programmer, which is what I am. Okay? So let's try to walk through this. It's traditional in a lot of tools that we end up using a bunch of functions taken from somewhere else. And so in this case, we're using a library called system, or sys, and we are importing it at the beginning. That's just letting the software know some of the stuff that's available in sys we need. If we leave that out and try to use the stuff from system, it's going to be frustrated with us. So we want to tell it up front, this is the system we're going to use. I'm a firm believer that if you are writing software, it's a good idea for you to tell people what the terms are for using it. Some of the things include things like, what is the name of this tool? I've chosen the name FASTA sniffer because to me, I always think of my old dog Panda running around in the backyard, sniffing at this or that. And that's what I want my software to do. I want my software to go to a FASTA file and give it a proper sniff, right? Programmers use very weird names. This is definitely true. If you ever want to look up an interesting story, I suggest you look up the name Apache Web Server because it's got a fascinating history behind it. All right, so we have FASTA sniffer. I believe it's important to talk about the version. Today, we're going to write version 0.1 of the software. By Monday, we'll have version 0.2. By the time we get to this, we'll be at version 0.6. But we'll call it done just the same. That too is traditional. I'm specifying it's by me. I'm at this university. And I'm also specifying the terms under which people are allowed to use it. The GNU public licenses are kind of an old school way perhaps to say, you can use my code if you want. If somebody wants to alter my code, they can download it, add a new feature to it, stick their names on as the second authors, and off they go, right? That's okay with me. If you're trying to write software that you're going to sell, like as a video game, don't make it public license like that. Unless you want somebody to take your stuff and sell it, which is okay too. All right, you'll note that sometimes I've used print with nothing between the parentheses. What happens if you do that in interactive mode? Let's come back here. All right, I'm just going to type print parentheses. A blank line. Sometimes the easiest way to get that result is just to run print by itself. You could write this more compactly. You could combine these statements into one line, for that matter. But here we're just writing it in kind of a spaced out strategy. Okay, so we are now going to use that bit from sys. Everyone remember that up here? We said we're going to import that library. This part is not all that friendly, and that's why I've just written it out. I hope you don't mind. So here we're grabbing something from sys, right? So sys is the big thing. From it, we're grabbing out the argv. These are arguments, okay? The arguments that were made when someone tried to run our script. So we are going to grab out the arguments that were passed to our script when someone ran it, and we're going to print the length of that to say how many different arguments were there when someone called our software. And then we're going to have the software output them to screen. And you remember that we did the str function applied on 5 and 6 to give us the number 11 in a string. In the same way, it's going to turn argv into a bunch of strings and spit them out to screen. Now, I'm going to try to show you how to run the script that we've created here. I'm gonna leave the other stuff for a moment later. So I'm still sitting inside the interpreter here. I need to get out of the interpreter and run my script externally. So I'm going to say quit with the brackets on it, right? With the parentheses. So having run quit, parentheses, I'm out. I'm back on the command line. Now you might think, oh my gosh, he's going to make us go find that software again. It's going to stink. But we're actually going to take a shortcut. Your computer remembers what you've been doing. Oh yes, it does. It has a long history of all these things you've typed. So if you hit the up arrow on your keyboard, you can see that it repeats the last command that you ran. The up arrow keyboard, the up arrow on your keyboards. So now I'm going to run Python, but I'm going to feed it some variables. All right, I'm going to feed it 2019-05-10. Wait, I'm a programmer, which means I'm lazy. So I'm going to hit the tab character, and we see that it has accepted the name of our software. Okay. So here's blah, 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 path Python exe, and then here is the name goal1.py, I believe it was called. It doesn't show up on my screen because I've got my fonts up so big, but it should show you the whole name on there. When I run Python exe with 2019-05-10 goal1.py, I see that it kicks out the information FASTA sniffer version 0.1, Dave Tab, Stellenbosch University, blah, 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 blah. How many arguments were passed to Python? 1. What argument was it? The name of the script that we're running. Everyone see that? Okay, so who was able to run the script from your command line? Yes, yes, good. Good. I tell you, dealing with the command line is actually one of the most irritating things about day one. So we'll get used to it with time, but we have to remember that when we want to run this script, we do it from this command line, and we do that. There are other ways you could go. It is possible, for example, on many operating systems, to drag your py file to the Python interpreter, or even just double-click the py file and it'll run. That's also feasible. But I'm trying to do it in a way that we can flip back and forth between the interpreter and running a script. Okay. So we see that we were just looking at this code, right? How many arguments were passed to Python? And it's telling us the length of the system arguments. And it was 1. We told it to tell us what was passed to the software. And here we see this one was here, what was provided right there. I'm going to try this by giving a few more arguments this time. So I'm going to rerun the script. And this time I'm going to say thing 1, thing 2, thing 3. So we see that sysv, the system's argv, each time is reflecting what we're passing to the software on the command line. Why would I bother with that? This might not be clear, but again, I want to teach you something useful about good programming practice. Could I write this script so that it automatically went to the FASTA file that I already know is in this directory? Of course. It would be so much easier. But the reality is, I'm trying to write code that someone may someday run on a FASTA file that I don't have access to. If I allow them to provide the name of the FASTA file on the command line, they can use my code without having to rewrite it. How irritating would it be if you, as a non-Python programmer, received this software and wanted to run it on your database, but you had to modify the source code to make it do that? We call that hard coding. Hard coding. If you hard code the name of the database into the script, somebody has to fix your script in order to make it run on other things. So we are here using the fact that Python can accept things on the command line as information within the software. So that when we tell the software on the command line, I want to go to this particular file and analyze it, they can do that without making any alterations to the Python script. Before today, how many of you realize that a .py file is something you could open in a text editor? We want our software to be useful to many other people. So making your software able to be configured at the command line or with a pretty user interface is a nice feature. Okay, how are we doing on time? Are you keeping me on time? It's 4 o'clock. All right. I'm not going to do much more, but I'm going to talk two seconds. We have a little bit of stuff going on here. And I want to explain what comes next. You see, we've received all of these arguments. We've now spit them out to the screen to say, this is what I saw. Next, we actually want to assign a variable in our code that says, this is the name of the FASTA file we're going to sniff. Right? So, I've created a variable called this FASTA. It's not a very good name. I could have called it FASTA to sniff, for example. I didn't. I just called it this FASTA. And you can see that I told the software it's a string because I said this FASTA is equal to, quote, quote. So I started out with a value of an empty string. Now, from there, I'm going to do a loop. Do you see this? The for loop? Remember, it's possible that I may have passed it multiple strings, as I just did. The name of the script, thing 1, thing 2, thing 3, those are 4 different string values that were passed in. And here, I can say, what is the first one? What is the second one? What is the third one? I can loop through all of them, and I know how many there are because I can take the length of that array of strings, of that set of strings, rather. And then I can come in here and look to see if the name of it contains .fasta. We've got some kind of crazy bits of coding going on here. I've told you that functions have the name of the function like print, and then parentheses and something goes inside those. But you see there's something weird about this what looks like a function I'm calling. Do you see this .find parentheses business? This is not a public function. This is a function that belongs to a string object. This is called a method. A method. So because systems args number 1 or number 2 or number 3 or number 4 is a string, I can run its find method to look for this .fasta business. Now, there are 2 major outcomes from that. One is that the file, remember I passed it thing 1, thing 2, thing 3? None of those say .fasta within them. So all of them are going to generate an error code when find is run. Find is going to return the value -1 to say .fasta doesn't appear anywhere in here. Now sometimes people use .FAA to represent a FASTA sequence database made of amino acids, or FNA if it's not. So we can also look for if it contains FASTA. FAA instead. Okay, so for each string, we're going to loop through all of the strings within sysargv, and each one of them we're going to check to see if it contains .fasta or .faa. If it does, it's going to set the value of this FASTA to that string. All right, now, so far, we don't know anything about whether these names correspond to a file that's actually there or not. So if I were to run this code with thing1.fasta, does this exist? It does not. There's only one FASTA file in the directory, and it starts with the name Mycobacterium, blah, 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 blah. So if I run this on thing1.fasta, the software sees that thing1.fasta does contain the FASTA string, and it sets the value of this FASTA to that. And as a result, when it gets out of that loop, it's going to say, this is the FASTA we will use, thing1.fasta. Okay, now there's another little trick. So I've passed over a whole lot of things here. We have some decision making that's going on in the software. It's using if and else if here to do that. I've already said -1 is an error code. It means that it went looking for that substring and didn't find it and returns a -1. So in each case, if it does find that substring, it sets this FASTA to it. Or if it finds .faa, that's also good. It'll write that into this FASTA. What happens if you provide multiple FASTA sequence database names when you run the software? When it encounters the first name, it will replace this FASTA with that. When it encounters the second name, it will overwrite the first name. So it's only going to operate on the very last one that we provided, the very last FASTA name that appears on its command line. So that's a little bit of a weird behavior. But there's something else. Remember, we have to be careful because our users are crafty. So I'm going to come back into my command line and repeat the command with thing1, thing2, thing3, but no FASTA files. You see that the software has now looked through each of these for .fasta or .faa, failed to find it every time. And as a result, it exited and it reports an error. No FASTA provided. Usage. The software will give statistics for the FASTA file provided on the command line, Python, blah, blah, blah. Here's how to use it. This is our usage information. You remember when we drew our flowchart, the very top exit says, if no one provided if the user of the software didn't provide a FASTA file name, we tell them how to use the software and exit. We've already accomplished that first bit of the flowchart. I want to note that the way that I figure out whether or not there's a FASTA that's been listed is that I check to see how long this FASTA is. If you remember, we started it as a blank string, which means it's got a length of 0. So we ask if its length remains less than 1, if it's a blank string, then we're going to go ahead to exit and give people a bit of information about how to use the software. I've done one other thing I should point out here. I don't want to belabor this too much. Here you see this command quit. Quit is kind of a rude way to close off your program. When you run a quit function within the software, it ignores the rest of the source code and just dies right there. So we're using this as a fast exit out of the software to say, don't do anything more, don't care about your variables anymore, just quit and die. So this is one of the ways that we reach the bottom, one of those purple ovals that appeared in the flowchart that we constructed at the beginning. So we start. We ask what arguments were used when launching the software. We check to see if any of them are FASTA files, look like FASTA file names. If they are, we accept them and move on. If they are not, we die. That's all we're doing with this first bit of code. Okay, so I spent a lot of time getting Python up and running on everybody's laptop. Hopefully, you'll remember how to launch the Python interpreter and so on in weeks to come. But for Monday, we're going to come back to this and keep building on this toolkit, learning a little bit about looping, a little bit about variables, and so on as we go. Okay? Thank you so much for coming. I look forward to working with you again Monday at 3.